So in order to do this, in order to go from the name to a formula, look at the first element. If it's a metal, then you know it's ionic, right? And if it's ionic, then you're going to assign charges to the metal and non-metal to figure out what the formula is. Take the charges and swap them, simplify that, tells you what the formula is. If it's a non-metal, if you have all non-metals, and hydrogen, then you know it's covalent. So in covalent, you're going to have number prefixes. So you will have di, tri, tetra, pent. That will tell you how many of each of them. So you will use those number prefixes to determine the formula. Carbon tetrafluoride, covalent, because carbon is a nonmetal. So with covalent, carbon tetrafluoride tells me that I've got a C and F. Tetrafluoride. Remember, if there's nothing in front of the first element, you know it's just one. Okay, you don't have to put mono in front of the first element. You only would put mono if the second element was one. So that one's just CF4. Lithium sulfate. That's ionic. Because lithium's a metal. Just look at the first element, find it on the periodic table. If it's on the left of the zigzag line, it's a metal, and you're doing an ionic compound. So we have lithium. SO4, sulfate, not sulfide. So when you see the sulfate, that's the polyatomic. So that's an SO4. The sulfate ion always has a -2 charge. So the lithium has what charge? +1, because it's in the first column. So you just take those charges and swap. The number of the charges tells you the formula. So this would be Li2SO4. The 2 of the sulfate tells you how many lithium. The +1 of the lithium tells you only 1 sulfate. So that help a little bit. Just going back over that. It's all chapter 3 stuff. Looking at structures of them. When you have molecules like CF4, carbon tetrachloride or tetrafluoride.
That's cool.
It's covalent. So you see the shape. What's the geometry about the carbon? If you have a carbon with 4 single bonds, what does that shape always form? It's the tetrahedral. Okay, so in the tetrahedral, remember, so you're going to evenly spread those fluorines apart from each other. Remember that fluorine being in that upper right corner is really the most electronegative. So the fluorines will pull the electrons towards each fluorine, not sharing equally with the carbon. But is this polar or non-polar? If you looked at one bond, if we just compared one to the fluorine, then yes. But when you look at that molecule, there's definitely the pull that direction.
Oh, uniform, they'll change that.
But can you see how it looks like the fluorines are evenly spread apart? So even though it has those really electronegative fluorines, because they're evenly arranged, it's a non-polar molecule. So if you have no electronegatives, or if you have electronegatives that are evenly spread apart, that is going to make it non-polar. Now, if you had the same thing, but instead of having 4 fluorines, you only had 1. I should use dots if I'm using dots. What would you say if you saw this? So in this one, see, when you only have 1 fluorine, can you see the electrons would end up like on the right side? And so those hydrogens on the left side would become more positive. So this would definitely set it up. The carbon tetrafluoride, though, because they're evenly spread, they like neutralize each other or balance the negativeness out of those electronegative fluorines. So this one would be nonpolar. Or sorry, this one would be polar. This would be polar compared to carbon tetrafluoride. Those last 2, that was the stuff that we ended with in chapter 3. That is doing grams to moles and moles to grams. And so if you want to know how many grams in 3.51 moles of vinegar, which is CH3COOH, in order to find that, what do you have to figure out?
How many moles are in 1 gram?
Other way around.
How many grams are in 1
Exactly. Yep. So you're going to look at CH3COOH. Look at the periodic table. Just add the mass of each of the atoms. So we have carbon, and there's 2 of them. They're listed separately, but there's 2 of them. We have hydrogen, and there's 4 of them. And we have 2 oxygens. Each carbon weighs what? And we're just going to round to a whole number. So take the mass, round it to a whole number. So each carbon weighs 12, so that's 24. Each hydrogen weighs 1, so that's 4. And each oxygen weighs 16. So times 2 gives us 32. Add those up. So there is 60 grams in 1 mole. So just take the periodic table, always take the mass, just round to the nearest whole number, add those up. So there's 60 grams in 1 mole. So when I do this, what unit do I put on the bottom? It's just a single unit conversion. Grams will go on the top, moles will go on the bottom. So 60 in 1. So I got 210.6 grams. So in this one, I tried to be a little better about significant figures. So 3.51, how many significant figures? 3. So I would take 210.6, and what would it be? 211. I'd keep these 3, the 2, the 1, the 0. The next number is a 6, so that would round the 0 up to a 1. So I'd have 211 grams. Okay? So that's just a single step, though. So if you have grams or moles, you can convert from one to the other. All you need to know is what's called the formula mass. It's just how many grams in 1 mole of whatever that substance is. But if you have moles and molecules, you don't have to figure out that. All you have to do is remember Avogadro's number, which is 6.02 times 10 to the 23rd. This is saying the same thing. 1 mole is 6.02 times 10 to the 23rd molecules. It doesn't matter if we're talking about vinegar, if we're talking about carbon tetrafluoride. It's just like the number of parts in 1 mole. So if I have 3.51 moles, this is what I'm given. What unit do you put on the bottom? The unit you're given always goes on the bottom in the first step. Molecules goes on top, and that tells you where you put your numbers. So 6.02 times 10 to the 23rd over 1. So moles and moles will cancel. 3.51 times 6.02 times 10 to the 23rd. So we got 2.11302, and then I have like a little 24 in small letters at the top. That means 2.11302 times 10 to the 24th.
My number above 19 is always 1 off. Even when I'm doing.
I think you're putting in times 10 to the. Are you using the EE button? Okay, so when you put it in.
Mine is always, every time I do this, is always 1 off. It's never more than 1, it's just.
So show me how you did it. So 3.51. Oh, no, you don't have to do, that's why. It's because you're multiplying it times 10. So all you have to put in is 6.02 EE, 23.
Okay.
So because you're putting in that times 10 to the, but that's really what that EE means. And that's why I really like you to have a calculation practice with it, just so that you can see. Is that what you got?
But yeah, the question about that though, why would you not have 1 sig big that answer?
Because this is 3. So 60 is from the periodic table. That's not a measured value. That's the measured value. Okay? So that's like, same thing like in unit conversions. Like if we went from grams to milligrams, you wouldn't take that 1,000 as being significant figures because it's really just changing the number. So you would go by what your measurement is. And so that 3.51 is considered the measured value. Did you get the right answer now? Okay. So we still have to round that to 3 significant figures. So 2.11302, just take the first 3. That means that the next one's going to get rounded. So it's a 3. So what happens? You just drop it off. Yeah. So 2.11. Don't forget to include the exponent though. You still have to keep times 10 to the 24th. You can't just round it to 2.11. Okay? So you do keep the exponent, but the exponent value is not part of the significant figure rounding aspect. So you still keep that. So 2.11 times 10 to the 24th molecules is what you would round that to.
So just for reference to whenever in the future, because I know they're terrible on these conversions actually in the exam. So when you're setting it up, setting this problem up too, it's always what's given.
What's given goes on the bottom in the first step. Okay? And this is just a single step. You don't even have more than one step to do with this. So whatever you're starting with will go on the bottom. If you're looking at grams and moles, then you're going to need to know the formula mass. So you just add up the mass of each of the atoms. If you're talking about moles and molecules, then just use Avogadro's number. Okay? Okay, so then that led us into the beginning part of chapter 3, which we talked about in lab. So if you were in lab last week, that was like your crash course in organic chemistry. And so you should find all of this in the catch-up so much faster. Okay, so remember that organic just means that it contains carbon and hydrogen. And we're really going to talk about the simplest ones. We're going to talk about relatively small molecules with just a few branches that are still super simple to name. So, while we talked about covalent molecules having that naming system, organic chemistry has its own naming system. Okay, so instead of naming like we did with the ionic compounds or with covalent compounds, when you name organic molecules, they went through and devised a base and stepwise process for naming. Always, you first start off with whatever the longest carbon chain is. So you may have just 2 carbons in a row, 5 carbons in a row, 8 carbons in a row. So that number of carbons becomes kind of the base name. If you have 1 carbon, then the base name will always be a meth. If it's all single bonds, which are considered saturated molecules, then they always end in ANE. So methane is just a single carbon molecule, all single bonds. Eth is the 2 carbon naming. So a 2 carbon molecule, all single bonds would be ethane. 3 becomes prop. 3 carbons, all single bonds, propane. Bute is 4. Pent, from 5 on, it's pretty normal. The first 4 are the weird ones. the ones that you really have to kind of like just commit to memory. Because it's pentane, hexane, heptane, octane, nonane, decane. Those are just like regular Greek like numbering system. The way that you draw them, and what you'll notice is that you always have whatever number of carbons you have. If you double that and add 2, that always tells you the number of hydrogens when you're just talking about the singlets. So for example, like propane, I have 3 carbons. So if I double that, it's 6 plus add 2 tells me 8. That tells you how many hydrogens. And it's because there would be 1, 2, 3, 4, 5, 6, 7, 8. So you would always have a hydrogen above and below each carbon, and then always those ones on the end. So those ones on the ends are why you always end up adding 2. So that is why, like decane with 10 carbons, double it, you get 20 plus 2. That's why you have 22 hydrogens. So there's a hydrogen above and below each of those carbons, and then those 2 that are on the end. When you're looking at the structures like this, remember this is the Lewis structure where you actually show all the lines. You can simplify it and you can put in what they call the condensed structure. The way that you read condensed structure is it tells you each carbon and how many hydrogens are arranged around it. So for pentane, it would be CH3, which means a carbon with 3 hydrogens, CH2, which means it's connected to a carbon with 2 hydrogens, CH2, same, carbon with 2 hydrogens. So it's telling you the links and how hydrogens are arranged around those carbons. Key thing to remember, hydrogen will never have more than just a single bond. Hydrogens are like always around the outside of these molecules. They're never like in the center. You'll never have a hydrogen spanning 2 atoms. It's only ever going to have a single covalent bond to it. And carbon's always going to have 4. So you're not going to see carbon without 4 bonds. So for us, we can make like ring structures, or we can make all of these branch looking structures, but the carbon's always going to have 4 covalent bonds to be stable.
Even if it's next to another carbon, it will be 4.
Yep. Always going to have 4, because remember it's in group 4. It has 4 valence electrons. It has to have a covalent bond to each of those valence electrons to make 8. The short way, the sort of quick and dirty way to be able to draw these, especially when you start getting into the bigger ones, are what they call that skeletal structure. So skeletal structure uses a line to represent each carbon-to-carbon bond. So in this, there's a couple of ways in the naming. The one that they show here, I don't think it'll let me, nope. The one that they show, here's the different ones. So if you do just a molecular formula, that's just the total number of carbons, total number of hydrogens, doesn't tell you anything about how it's put together. That's what they call molecular. Condensed is when you have the carbons and how many hydrogens are arranged around each. The Lewis is the one that takes forever to draw, but the Lewis structure shows you every single covalent bond as a link. The skeletal structure here, this is a carbon atom, this is a carbon atom, this is a carbon atom. So you can see in propane, 3 carbons. So all you'll see, it would be 2 lines. So the key thing in remembering with skeletal structure, it's the number of carbons minus 1. That's how many lines you will have. So for example, with octane, which has 8 carbons, you would only have 7 lines. So in your zigzag, just count 7. Okay, because there's always 1 on each end and 1 at every corner. Skeletal structure doesn't show carbons. Skeletal structure doesn't tell you that there's hydrogens, but they have to be there. If there's carbon and you only see that it's got 2 lines coming off of it, then you know it has 2 hydrogens as well to give it its total of 4. End carbons always have 3 hydrogens. Middle carbons always have 2 in order to create that stability. So you can see in this first one, Lewis structure going to skeletal structure. Lewis structure for butane has those 4 carbons, but notice that there's only 3 lines when you draw the skeletal structure. And we're not going to draw those, so I don't know why they even put that one on there. Naming. So we did start the naming, and so I did go back and redo like the worksheet thing that I gave you in lab. So now you have another, sort of like another one. So has everybody got one?
No, not anymore.
Hmm?
I'm not in lab.
Yeah, so that's why. So I knew that there were some people that didn't have to take the lab, and so I gave this out in lab and we kind of walked through some of it. So I went ahead and just redid it, and I have some practice ones so that we can work on both naming structures and then also drawing structures from the name. So in this first page, when you name an organic molecule, you will see that there may be just a straight line of carbon. It's pretty simple then. If it's like straight line of carbons and there's 5, then it's pentane and you just move on. But on some occasions, there are non-hydrogen groups that are hanging off of the main chain. And the main chain just is the longest chain. It's not always the one that's in a straight line, but it is the longest. So in this one, this upper left one, when looking at, can you see that 5 carbons is the longest chain? Now, it wouldn't be wrong in this one if you actually started here and went this way, but that's not the way I numbered, so we're just going to go the other way. Okay? So you find the longest carbon chain. Sometimes you may have to go around a bend or two. That's going to become the last name. So 5 carbons, we said, is pentane. So that's the last name in its organic molecule. Second thing is there anything other than hydrogen connected to the chain? Yes. Okay, so we have this. Notice all of the others are hydrogens. You don't have to name the hydrogens. All you have to do is name the non-hydrogen groups. So that group I have on here, it's a non-hydrogen group. If it has a single carbon, we said 1 carbon is meth, but if it's a single carbon hanging off, then they call it a methyl. So this is a methyl group. Okay, so number 2. Are there any extra non-hydrogen groups in the molecule? Circle them and name them. If it's just a CH3, which is what this one is, that's just a single carbon, so it is a methyl group. If it was a CH2, CH3, or 2 carbons kind of like hanging off like a little mini chain, then that would be an ethyl. Just like we said, meth was 1 carbon and eth was 2 carbons, so it would be an ethyl. If there were 3, which would be a CH2, CH2, CH3, like 3 carbons as a chain hanging off, that would be a propyl. So I've got those ones listed, and really there won't be any ones bigger than that. But now, to indicate where that methyl group is, I have to number the chain. And all I'm doing is just numbering the chain from right to left or left to right. You're going to number from the end, and the rule is number, this is step number 3, number the longest carbon chain starting with the end closest to the branch group, closest to the non-hydrogen group. So in this, which side is it closest to? The left. And so this is why you would go and number 1, 2, 3, 4, 5. So the number that I put in is just numbering the chain because I need to say which carbon does this methyl group hang off of. And you would say it hangs off of carbon number 2. So you put a number in front of the group. That tells you which carbon it is attached to. And that's the name. There's no other ones, right? Everything else is just hydrogens. If you look all the way around, so you would just call this 2-methylpentane.
So it gets easier when you do it too many times.
Huh?
It gets easier when you do it too many times.
You keep practice. It really is the practicing thing. Okay, so looking at this one underneath. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 carbons in this molecule. Okay? But what's the longest carbon chain?
Second.
I see bigger than that. How long is the longest carbon chain? How many carbons?
3.
No. No. I see one with more. Where do you start? Down at the bottom. Look at this. How many? You see 8? Okay, so if it has 8, that makes it. Okay. So that accounts for all those carbons. So do I have any non-hydrogen groups hanging off of that chain? Yeah. I have this one. This is a CH3, so that's a methyl. This is a CH3, so it's a methyl. And this is a CH3, so that is also. So now, I found them all. All the rest of the stuff's just hydrogen, so you don't have to worry about those. I just have to figure out, okay, so I've got 3 methyl groups. Which carbons are they attached to? So start from either side. I want the lowest possible number combination. So if I go 1, 2, that would make this one 3, right? And then this one would be 4, 5, 6. This one would be 6, 7, 8. Okay, so I have 3, 4. This is a 4. That doesn't look like a 4. I have 3, 4, 6 methyls. All right, let's look at the other direction just to check. So what if I go this way? 1, 2. Okay, so this will be 3, 4, 5. So now this one will be 5, 6. This will be 6, 7, and 8. So which is the lowest? So 3, 5, 6 or 3, 4, 6? The purple. Okay, so do you see how numbering it the other direction, it's not as low? You always want the lowest possible number combination. So the way that I put this is 3, 4, 6. They're all methyls, but there's 3 of them. So IUPAC said, those are the people that made up these rules, not me. So they said you can bundle them. Okay, if you have the same non-hydrogen groups, you can group list them all together. So I don't have to say 3 methyl, 4 methyl, 6 methyl. I can say 3, 4, 6 trimethyl octane. So I just group all the methyls together. The numbers tell you which carbons they're hanging off of. And the tri is very redundant, but that's how they said to do it. Because the tri tells you there's 3 of them. 1 on carbon 3, 1 on carbon 4, and 1 on carbon 6. So look at your handout, flip your page, or look at that bottom page. Look at the bottom page. We'll do those first ones, and those are all Lewis structures because they show you every single bond. You have that one. That's the second. So down at the bottom. Well, that's from there. There's that one then. Okay, so looking at this, I think I have it. What's the first one? It's just pentane, yes? See that it's 5 carbons in a row. No groups hanging off. Where are you? Here it is. Ding, ding, ding. Almost there. So this one, we can pen it. 5 in a row. Pentane. Do you need anything else?
No.
No. You don't have to name the hydrogens. You know that they're already there. Okay? What about the next one? Okay, longest carbon chain, first step. Longest carbon chain, 4 in a row, which makes it a butane. So this is butane. Then I have to name this, which is a CH3 group hanging off. So this is a methyl group. The last thing is I've got to figure out what carbon is that hanging off of. So if I start and number from this side, 1, 2, 3, 4, it's hanging off of carbon number 2. If I started from the other side, it would be off of carbon 3, so you want the lowest possible number combination. So 2-methylbutane. What about the next one? What's the longest carbon chain? 3. Okay, so you could go this way. I always look for the flat line first, like straight across if I can help it, okay? But you wouldn't, it would not be wrong if you did this, okay? Because still it's 3. So either one's fine. So we go 1, 2, 3. So if it's 3, that makes it a propane. So this is a methyl. This is a CH3. This is a, which is a CH3. And they're hanging off of carbon number what? Do you see that they're both hanging off of carbon number 2? So that's a 2-methyl, and this is a 2-methyl. So you would call this 2, 2. Since there's 2 of them, you use dimethyl. 2,2-dimethylpropane. So in looking at this one, this is also considered a condensed structure. I try not to draw them out this way because that's always, to me, it makes it look like the bromine's in the chain. But remember that bromine's in group 7, so it's only ever going to have a single bond. So if you look, you see CH3, CH2, 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 CHBr, which means that this carbon here has a hydrogen and a bromine. So that's what that, see the CHBr? So there, that carbon has a hydrogen, and I'll just put the hydrogen down, and then it has a bromine sticking up. And then it just continues the rest of the structure. So you might see something drawn like this, especially if you're looking in a text, and they're just trying to get everything on the line. Instead of doing a down line or an up line, you might see it written out that way. So just take and spread them out. You know that hydrogen can only have one single covalent bond, and you know that chlorine, fluorine, bromine, and iodine will only ever have a single covalent bond. So they'll never span 2 carbons. They'll always be kind of like a hydrogen around the outside. So that's what that means. So now looking at it, longest carbon chain. So this is, what is 8? Yeah, octane. Okay, so we just named this. So that means that we have this hanging off. So this is a bromine. This is the only other non-hydrogen group that you'll have to worry about naming. Bromine, chlorine, fluorine, and iodine in group 7 only ever form a single covalent bond. And so I have that on the front. If you have a bromine attached to the chain, you're going to call it a bromo. If you have a fluorine, it's a fluoro. If you have a chlorine, it's a chloro. If you have an iodine, it's an iodo. So this one is a, it's just like we did with the methyl. Find any non-hydrogen groups, circle them, name them. And really it's going to be methyl, ethyl, or one of the halogens. Those are pretty much it. There's a whole lot more it could be, but those are the only ones we're going to work with naming because it keeps it pretty straightforward and simple. Okay, so we're going to have to number. Do we number from the right or the left on this one? The right, because it's closer to that end. Okay, the bromine is closer to the right side, so you would say it's hanging off of carbon what? 3. So it's 3-bromooctane. When you're looking at and naming skeletal structures, like look at this one. When looking at skeletal structures, remember every corner and every end is a carbon. So how many is that? 7. So you see 7? So every corner and every end is a carbon. So 7 is? Nope, that's 8. Heptane. And so you see nothing else off of the zigzag line? There's hydrogens there. But you don't have to name those. You automatically know those middle carbons will have 2 hydrogens. The end carbons have 3 hydrogens. Carbon's got to have 4 covalent bonds to be stable. But in a skeletal structure, they don't put it in there. So you just remember that doesn't mean that there's nothing but carbon. There's still hydrogens in there. But we don't have to worry about naming them. Just a really quick way of being able to draw them. All right, so what's this one? This one right here. What's the longest carbon chain? So it is pentane. Now on this one, we do have a hanging group. So it's called what? Chloro. So we have a chloro. So right to left, left to right, or does it matter? It doesn't matter. So either way, your chlorine is going to hang off a carbon what? 3. So if I went 1, 2, 3, 4, 5, every corner and every end is a carbon. What about this one? Longest carbon chain. So see here. So that's 1, 2, 3, 4, 5. What is this? That's 5 too. So that wouldn't be wrong if you decided to call those. Same thing here. I'm just one that tries to stick to the straight if at all possible, just because it makes it clearer to me. So again, this is the pentane. So what is this? No, it's a what? What's this group hanging off? It's got a corner and an end, so it's a 2-carbon group. That is a ethyl. So that's an ethyl group. And it's hanging off of carbon number what? 3. Just like the last one. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Either way, you're going to have a 3.
I'm sorry, how you get ethyl again?
Okay, so because it comes down, this is a carbon and this is a carbon. So it's a 2-carbon group, so it's a CH2, CH3 hanging off. If it was just a line coming off, then that would be a methyl. So like if it was like this, that would be a methyl group. Just a single line sticking up would be a CH3. But see how I have a line with the bend? Then that means there's 2 carbons. Every corner and every end is a carbon. Okay?
I'm blanked out there for a second.
All right, so what about the rings? So with the rings, the last name is the number of carbons in the ring. So that one has how many carbons make that ring? 5. And you use the term cyclo. So the end name, when you have a ring structure, the end name starts with cyclo and ends with the number of carbons in the ring. That is a cyclopentane. It is a 5-carbon ring. So we named all of this. Yeah. Okay. So then the only other thing is yes, it does have something hanging off. So we've got this, which is a CH2, CH3 group. This is a carbon and that's a carbon. So it's a 2-carbon group hanging off. So you call it ethyl. So in the numbering part, we don't have an end because it's a ring structure. So you always start numbering on the hanging group to give you the lowest possible number. So you would number here. So this would be 1. And it wouldn't matter if you went clockwise or counterclockwise, the ethyl is still hanging off of carbon number 1. So it'd be 1 ethyl cyclopentane. if there's one, usually they leave that off. They would just call it ethyl cyclopentane because clearly it would have to be on the one because it's the only one that's there. Hmm?
But tell me how you get the
Uh-huh. Okay, so if you have a ring, the last name is going to have cyclo and the number of carbons that makes the ring. So that's why it's cyclopentane. So that way, anytime you see cyclo, you know you're going to draw a ring. So cyclobutane would be a ring with how many carbons? Butane. 4. Okay. Cyclohexane would be a ring with 6. Cyclooctane would have 8. So if you see cyclo, whatever the name after is, tells you how many carbons in that ring. All right. So since we're doing the cyclos, what's this one? It is. So this is a it's a ring of 5. So you've named, in doing that, you've named this. But you still have to name any non-hydrogen groups hanging off. So this, even though it says H3C, it's really a CH3. So it's a methyl. What's this one? It's also a methyl. And then this would be a, yeah. All right, so I have 2 methyls and a chloro, and I've got to number them. So in trying to figure out the numbering, I'm going to number the ring, and I want the lowest number combination. So where would be the best place to start? Okay, so if I started on the methyl and I said 1, 2, 3, 4, 5. So if I went clockwise, then that would give me a 1 methyl, 2 chloro. Yes? Now if I went and did it the other way, so if I said, okay, well I'm going to start here and go 1, 2, 3, 4, 5. If I went the opposite way, then this would be a 1 chloro, 2 methyl, 2 methyl. Okay, you're always going to start on a hanging group and a cyclo. It's just a matter of figuring out which hanging group to start on and which direction do you go around the ring. And so just look at each one. So what would give me the lowest numbers, the blue or the red? The blue. So the blue is a 1, 1, 2. The red would be a 1, 2, 2. So I would pick the blue. So this is going to give me the lowest numbering. And that's just the way that you can be kind of consistent with it. So I have 2 methyls and I have a chloro. So with step number 4 that we haven't really had to deal with too much, step number 4 says if you have multiple non-hydrogen groups hanging, you list them alphabetically. So which one do I list first? So chloro gets listed first. So it would be 2 chloro. And then how do I do the methyls? Put 1, 1 dimethyl, because remember that means there's 2 methyls, one on carbon 1s. Just each time, same steps. Just find longest carbon chain or the ring, that's the last name. Circle the groups, name each group, and then figure out your numbering. And then just when you list them, just list them alphabetically. So this one I did, I think I was getting tired. So this would be CH3. This would be CH. That's just that. That's a CH2. This is a CH3. I just didn't put the hydrogens on. I think I got tired of it. I was trying to draw molecules and I was like, to heck with this. I'm just putting the carbons. So there, I just put them back in for you. Okay. So longest carbon chain? 5. Do you see 5? 1, 2, 3, 4, 5, all the way across makes this a pentane. So then this group hanging off is it's a chloro. This group hanging off is a chloro. This group hanging off is a methyl. That's why I said mostly it's like methyl, ethyl, chloro, bromo, fluoro, and iodo. Those are pretty much like the non-hanging groups, non-hydrogen hanging groups you have to worry with. So numbering, do I number from the left or the right, or does it matter? Why do you want to number from the left? So see, chloro is closer to the left, the first chloro. So this would give me a, if I go 1, 2, 3, 4, 5, that makes this a 2, this a 3, and this a 3. If I went the other direction, it would be the 3s would be fine, but that chloro would be a 4 instead. So you do want kind of like, sometimes you just look at the end and kind of count in until you get to the first branch. It tells you which side to number from. So which do I write first? So I have 2, 3 dichloro, and then 3 methyl.
It wouldn't matter about the 2 and the 3. It's just two different.
What that tells you is that there's a chlorine on 2 and a chlorine on 3. So now what I want to do is I want to go back and do some drawing from a name. Okay, sort of like working the opposite way. We'll come back and look at these ones next time, but go to the next page. Not there. Here. So when you're going to draw a molecule from a name, you have a couple of choices. Like you could do condensed, you could do Lewis structure, you could do skeletal. So there's some variations. So in this, when you go to draw the molecule 1, first put in the longest carbon chain. So you got to look at like the last name.
Last part, yeah.
So in this one, I see
5.
Okay, but what else? It's a circle. It's a cyclopentane. Okay, so cyclopentane tells me I have to put 5 carbons in a ring. And I'm not super picky about like I make mine look like a house. I'm not super picky that they are like perfectly lined up and everything. But there's the cyclopentane, and then I have an ethyl.
2 extra carbons.
So that means that I have to put a 2 carbon group hanging off somewhere. So that's kind of like the framework of it. So then you can add the hydrogens in. Every end carbon, like at the end of the ethyl, would be a CH3, because you notice it's got 1 line connected, which means the other 3 would be hydrogens. In the ring, because every carbon's connected to 2 carbons, those carbons would have 2 more hydrogens. So you see there's CH2, CH2. The one where the ethyl group hangs off, can you see that there's like 3 lines connected to that carbon? That's why you would have 1 hydrogen on that one, because it's going to give you a total of 4. In all cases, the number of dashes and the number of hydrogens, or the number of groups connected to carbons, would need to be 4. (3,3) difluoro 2-methyl octane. Just start off and go 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's just adding them in, okay? Just lays down sort of like these are your carbons, okay? I always, when I do this, I always just automatically will number from left to right, just because that's like the normal numbering pattern. So when you add those in, then this is carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, and 8. And so 3,3-difluoro means what are you going to put on? Where? I'm I'm going to put a fluorine on carbon 3 and a fluorine also on carbon 3. That's why it's 3,3-difluoro, means 2 fluorines both on carbon 3. And the other one? On carbon 2, I put a methyl, a CH3. Anything else? You have that look on your face. Why are you looking like that? All right, which part in that step? That's the only thing I want to make sure. So you look at the last name to tell you the number of carbons, number it, okay, and then just go through and add. So 3,3-difluoro means I'm putting 2 fluorines both on carbon 3. So the 3,3 tells you the carbon in the chain they hang off of. And then 2-methyl means I'm going to put a CH3 on carbon number 2.
Okay, I got
Okay.
it. But then isn't it another 3? Okay.
What do you mean another 3? So 3,3-difluoro means you're putting a fluorine on both on carbon 3, because it's difluoro means there's 2 of them. All the rest of these, if you really wanted to put these on, all of these would be what? Hydrogens. Okay, so all those lines, those would all be hydrogens. If you had to draw the Lewis structure, you would go back and add those in. If you wanted to draw this in the skeletal structure, then starting with octane, where you put your pencil down, count that as carbon 1, because remember that's at the end. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8. Right, so do you see 7 lines? Ooh, they're gone. They were here. Hold on.
Why is that CH3?
It's a methyl, right? Remember, it's a single carbon. CH3 is the single carbon group methyl. Where see how this one is a CH2 CH3? That's an ethyl. So if it was this, that's a methyl. Okay, so just the difference between the two. So 1, 2, 3, 4, 5, 6, 7, 8.
So you
Okay.
count 7 when you're doing the lines, though.
Yeah, 7 lines,
So you
but
go
it's,
1,
but I always say 1 as I put my pencil down. And then so I've like, where you're putting your pencil, that's carbon 1. And then every corner is a carbon. So I always start 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's octane. So if I was going to put a methyl, this, if you're looking at the way that these are numbered, this is carbon 1, 2, 3, 4, 5, 6, 7, 8. So if I have 2 fluorines off of carbon number 3, you could put a fluorine here and a fluorine here. One up, one down. And then what's the only other thing? And so a methyl will look like this. It'll just look like a line sticking up. So just a single line sticking up is the methyl. Off of carbon number 2. Just another way to draw it, like if you see the skeletal structure, to be a little more familiar with what you're looking at. Two methyl, 3-propyl heptane. So when you see heptane, what are you going to put? 7 what? 7 carbons. 1, 2, 3, 4, 5, 6, 7. There. Got the heptane part down. Then 1, 2, 3, 5, 6, 7. 7 carbons in a row, number 1 through 7. So that means that I've got to put a CH3 here.
Would it matter if you put it up or on top or bottom?
But it would be like that. That's actually wrong. Okay. All the rest of those would be just hydrogens. But they're still there. That's why I put that. Don't forget, there's still, carbon's going to have 4 covalent bonds. So if you don't have a carbon or a non-hydrogen group, it's going to be a hydrogen that's on there.
Carbon 10, you don't count out Count off if y'all
I will,
try.
on the test, I'll actually tell you like what structure. So I might say, use the condensed structural formula, draw this. Okay? So like if we're going to do the condensed, and for me, I would have to turn around and then redo my formula and add the hydrogens and write it in a condensed way. So if I was going to do that, I would look at this and say, well, I have CH3, CH, put my line up, CH, put my line down, and then CH2, 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 CH3.
So that's how you do the condensed.
If you're doing condensed, the only things that hang off are branches, okay? I don't do the condensed with them all in the long chain because I think that that looks really confusing. But in that, you can see which the hanging groups are, okay? So that's how you'll see that. So you see how this and this are exactly the same? The condensed just tells you how many hydrogen are around each carbon. The longest carbon chain is all in a row, and then you have the lines hanging off. Those are the non-hydrogen groups. So, 2-iodopropane.
3 carbon.
Because it's a propane.
And then you have the iodine.
Yeah. Anything else? Yeah. Just put your base and then just add the non-hanging groups. Those would be hydrogens. Na, 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 na. Okay, last two. See if you can write them out. I'll give you, like, you do them. You just got to add your hydrogens in. Little spaces, but yep, that's the exact. Because you look at pentane and you say, okay, I'm going to put in 5 carbons. And so I have 1, 2, 3, 4, 5. And then it's 2,3-dimethyl, which means what? Put a methyl off of 2. So methyls are CH3s and they could both stick up, they could both stick down. You can have one up, one down, doesn't matter because these have like free rotation, so they don't just sit still, they could all flip about. A lot of times you'll see them drawn like this just because it gives you a little more room. Like you'll see people have like one it'll be sticking up, the next one will be down. That doesn't matter. Okay, we haven't gotten to stereoisomers yet. Last one, it's just a butane, so it has. It's just a wee butane. And yeah. They're really not too bad. It's not like the back and forth type of thing. You might see 1, 2, 3, 4, 5. Looking at this one, skeletal structure would look like this. Skeletal structure like that.
It's just sometimes the wording makes it sound difficult. It's just the wording.
Yeah, the wording does sound super complicated, and you're like, oh, that's not all that bad. You just look at the last name first. That gives you the base chain. just number it. I always go left to right just because that's straightforward. And then just drop the methyls or the ethyls or the chloros or the fluoros off of whichever carbon number comes ahead. And just that try just tells you that there's 3 chlorines total, which seems pretty obvious because you have 3 numbers. Like, that seems redundant to me. It's my only argument against the IUPAC people. So IUPAC is the International Union of Physicists and Chemists, and they are the ones that came up with this naming. And so it's like, that way it's consistent across the world. No matter whether you're speaking in French or if you're speaking in English, it's still the same process, the same steps of naming, because it used to be that people had like all their own little naming ways. And then that way, like, you didn't know what people were doing. And so this actually put it all kind of in the same. Okay, so what we're going to talk about next time, so keep this. You've got like 3 more molecules here you can go through and name. Keep this. This is a good sort of just summary on how to do this. Next time we're going to talk about isomers. So this naming comes into play in being able to identify molecules that look similar but may have different bond arrangements. So we'll talk about conformational, structural isomers, and then the stereoisomers. And then we can go on and finish chapter 4. Hurry up.